Hello everybody, I am Cédric Bellanger from Marketing Communication Department. And today I'm very pleased to co-present this webinar with Vincent Hourdin, PhD R&D engineer in VR, and Stéphane Coincy, VR experience product owner. First, a few words about OPTIS. OPTIS, a world-leading company in virtual prototyping, provides simulation software allowing you to accurately simulate the performances of light, human vision, and material interaction, ultimately allowing you to experience your product virtually before ever spending the time and money to build multiple physical prototypes. So thanks to OPTIS, you can imagine, design, and virtually see and hear what you will get during all stages of the design, engineering, and manufacturing process. The summary, I will start with the trends and challenges and will carry on OPTIS proposal, OPTIS vision, then Vincent Hourdin will open the topic of our solutions dedicated to HMI development, and Stéphane Coincy will close the topics and explain how you can join our early adopter program. Airbus A320, launched in 1988, reached a milestone in aeronautics history. A320 is the world's first airliner with digital fly-by-wire flight control system. The HMI shows innovative features. Multiple sources of information can be taken from one interface. Here, for example, the digital altitude indicator. It is the first wide-body aircraft designed to be operated without a flight engineer, only by pilots. A320 interfaces become standards, and all following Airbuses and aircrafts from the competition till today have similar human-machine interface and system control philosophy. These interfaces give a full control to the pilots, but they are fully loaded. The complexity of the machine is transferred to humans pilots. The report from Boeing Aero magazines on the causes of accident is clear. In the early days of flight, approximately 80% of accidents were caused by the machines. Today, that statistics are reversed. Approximately 80% of airplane accidents are due to human error. Air traffic controller, mechanics, and pilots for 80% of the cases. These errors are due to misunderstandings of the aircraft, misunderstanding of the HMI. So aircrafts incorporate reliable and advanced technologies, but HMIs overloaded are lagging behind and does not assist the pilots properly. In automotive, HMIs show advanced electronic features, but a 2016 consumer report described it as high-tech headaches. HMIs are complicated to use for the older drivers, while the youngers find problems using them. Interfaces development in automotive is a conundrum for automakers. Trying to stay relevant to car buyers whose lives are increasingly centered on their smartphones and other connected devices, here in yellow, but at the same time remaining mindful of a driver distraction problem that is already a factor in up to 30% of road accidents in the European Union, according to a 2015 report by the European Commission. So in aviation, like in automotive, HMIs have evolved to give a full control of advanced machines, but the complexity of these machines has been transferred to users, drivers, and pilots, and this is generating safety issues. The future will hide complexity and show simple, intuitive interfaces coupled with smart virtual assistants. The technology will be based on screen sensors to interact with humans and artificial intelligence. What is OPTIS proposal? What is OPTIS vision? At OPTIS, we enable our partners in delivering innovative designs that have been tested and optimized for their final customers. We assist our partners in many aspects, including safety, ergonomics, and perceived quality. This translates to several topics: color and material choice and uniformity, human-machine interface development, interior lighting, exterior lighting, and the current hot topics of HUD and globally advanced driver assistance system and autonomous driving. Basically, OPTIS enables innovation for our partners anywhere lighting, human vision, and sensor vision are involved. The key difference of OPTIS proposal is that our powerful design platform offers a tangible decision-making solution. Don't wait until it's too late for the surprise of bad consumer reports or ratings. Create a virtual prototype and in the beginning, share a scale 1 true-to-life experience in virtual reality with the makers and with your consumers. First, improve the collaboration, the concurrent engineering among the different teams internally and among the business partners, OEMs with suppliers. Secondly, listen to the voice of the customers. From the early concept phase and throughout the development, focus on the perceived value of your innovations. Bring the value where it is the most appreciated by the targeted consumer. Thanks to OPTIS combination, design, and decision-making platform, you deliver the right innovations that reach the customers. Now I will let Vincent Gourdin, PhD R&D engineer in VR, detail our solution dedicated to the development of smarter interfaces.
Thank you, Cédric. So our solution is a virtual reality platform in which new designs can be quickly evaluated in a realistic situation. We have an external environment that provides the immersiveness. The internal environment is interactive, featuring dynamic displays and finger-controlled elements. The vehicle is managed by an external simulator, ensuring its realistic behavior. All this has one goal, and that is evaluating how a user is interacting with the new system, may it be a single interaction element, display content, or a completely new cockpit. Human factors are evaluated much faster than traditionally, and no physical prototype is required, hence a much lower cost for each new simulation. The video you are seeing shows the prototype of the iVision project. It was a European project initiated by the end user, EADS Innovation Works, now called Airbus Group Innovations, to study how virtual reality could be used to validate human factors related to commercial aircraft cockpit designs. The project is now finished since 6 months and showed that virtual reality can help a lot, greatly reducing the cost of human factors analysis in a complex environment. We are now using similar techniques to evaluate human-machine interactions in a car cockpit in a virtual reality driving simulator. In this video, the external environment and aircraft controls are provided by the flight simulator, while in the driving simulator, a third-party software provides elements for the external environment, car dynamics, and also the traffic and pedestrian. In cars, we also have a new way of interacting, which is the touch screens. And as you can see here, the simulation is done in a cave system with 3 display walls in stereo, but it could as well be done in a head-mounted display, which is cheaper and even better for finger-based interactions because the physical hand does not mask the virtual hand. So the goal of this European project iVision was to help designers and analysts with the study of human factors, and it's still the case with the new human-machine interactions. We can outline 3 categories. The physical ergonomics, with the reachability of all cockpit elements computed using mannequin algorithms, as illustrated on the left, and with visual ergonomics, which includes many different features like field of view analysis, readability evaluation, brightness levels, reflections, and so on. The cognitive ergonomics is centered on task analysis, and it can give information on workload and safety using methods such as critical time analysis, self-evaluation, or error detection. Then the visualization of this data can be used for ergonomics as well, as shown on the right with a part of a workflow of tasks with the green arrows. And then the attractivity and adoption is focusing on the look and feel and the user experience. So let's continue with the visual ergonomics. Visual ergonomics is very important because vision represents about 85% of human perception. And OPTIS simulations, as you can see, are able to reproduce day and night veiling glare, but also screen washout, retro reflections, aspheric mirror reflections, reflections on windows, readability and legibility of displays, and the effect of various lighting conditions. We also have field of view analysis, as depicted here on the top from the cockpit of a helicopter, eye adaptation and readability of cockpit displays depending on night conditions. It's very important because it's a real challenge, for example, for pilots to move from instrument flight to visual flight and reverse, because the light conditions can be very different. And so we have seen that vision is very important because it's estimated as 85% of our perception. But according to Francis Ford Coppola, half of what you see is what you hear. It means that hearing counts as half of what you see, and that what you see is influenced by what you hear, and vice versa. So auditory ergonomics is very important as well. And for example, we have two main aspects at stake for the auditory ergonomics. The first is very well known, relates to hearing feedback about what you are doing. For example, you don't necessarily see the signal of the turning light, but you can hear it in your car. Our software can help you design the sound so that it's best heard, or so that it feels better in a noisy environment. The second aspect is that it's critical to detect and neutralize a noise that could affect the behavior of the driver from a safety standpoint. HVAC generates a lot of noise that can disturb the driver and even cover the noise of external environments, such as honking of another car or a shouting pedestrian. A good example that we have is the story of a helicopter pilot who was frightened by a loud and strange noise coming from a poor HVAC, and it was a kind of shock that evoked a malfunction or breakage at ignition. Our software is able to isolate such noises and would help the designers improve the noise of each subsystem. Then about the cognitive ergonomics, I will show you what we had in the iVision project, the European project. Here is an example of how such a tool can help tremendously designers and analysts. Usually, recording what's happening in a simulation was done manually with pen and paper and required a lot of knowledge of the analysts. Now, with VR, virtual reality, actions done in the simulation are automatically detected and logged and appear in this interface as the green boxes below. You can see it happen in the video on the screen that is on the floor. The green boxes appear at the end of each interaction. These interactions can be finger or eyesight interactions with a cockpit element, but also system information changes, such as enabling autopilot or reaching a speed threshold. The analyst then takes these appearing boxes and represents them to high-level goals that were already defined for a given simulation, and a considerable amount of time is saved to create a hierarchical task analysis, or HTA. And then from this HTA, as actions are detected in the current simulation, in a new simulation, we can evaluate how well the task is performed by a pilot, or if deviation occurred. And the system can also indicate the current active tasks for training purposes, possibly in VR. The hierarchical task analysis can also be replayed by a mannequin as a list of tasks, and this mannequin could act as a co-pilot also for training purposes. We can also imagine that we introduce errors in the hierarchical task analysis to see if a human trainee will detect the errors of the virtual pilot. So based on this hierarchical task analysis representations and the metadata it contains, other powerful tools were implemented, like critical time analysis that computes the shortest time in which a flight procedure can be done. Self-evaluation uses questionnaires at the end of a simulation to get feedback from a pilot and have insights about his feelings. Error detection helps computing likelihood for potential errors in the design based on rating of independent actions. And finally, the engineers can use some special requests on the system, such as highlight the cockpit elements that were turned by the copilot during the landing simulation, so very complex sentences, or show the workflow for hierarchical task analysis for a given hierarchical task analysis. So that would draw the arrows in green here in the virtual reality view and allow the designer to quickly see what the workflow for necessary to compute a particular task is. And as an aid to cockpit designers, the tool shall also allow cockpit variants to be compared. An overall grade can be given to a cockpit variant depending on all of these human factors evaluations. And now Stefan will tell you more about the attractiveness and look and feel.
Thank you. Thank you, Vince, for those insights. So far, we have talked about physical ergonomics, how you see and interact with product, and cognitive ergonomics, how you understand, apply, and remember the use of a product in an efficient manner. But this is not everything. What about the design, the look and feel of your HMI? Almost all industries are being disrupted by digital technologies, as you know. Smartphones and tablets are everywhere. The experience they deliver has become a standard, an expectation from all of us. Now your customers want to use intuitive, beautiful, and fun HMI, and they expect this at the core of any product they purchase. As such, VR must allow the simulation of the newest HMI concepts in the market, such as the touch screens. You can reuse your HMI digital assets in VR and interact with them as you would do in actual driving conditions. On another side, all industries are heading to smarter and smarter devices, but that trend requires new tools to cope with that increasing complexity when developing a new product. And to do so, VR is the ideal technology because it can put everything in context: product, environment, and the human, enabling teams from diverse expertise to share content and understand each other. VR allows you to see and interact in a natural way with your product, facilitating decision, thus accelerating the product development cycle. For example, you can see on the left a sensor example. The body in white expert, the vehicle architect, and the ADAS expert can see the sensors at play for assisting the driver with parking. And they can envision several scenarios to pre-test the system and assess the impact of the vehicle shape in regard to the sensor's capabilities. On the right side, you have a pixel beam example. The lighting engineer, the system engineer, and sensor expert can test your intelligent lighting in many different situations, not only varying the car design and environment, but also the driver's behavior. You can pre-test accurately the impact of that system on the behavior of the driver to come up with the best solution. From another aspect, having the end user in the loop will help you to validate new concepts as early as possible in the product design cycle. Here on the left side, you can see that someone sits in a bug and acts as if he were in a real car, trying to feel the roominess of the car and access the car dashboard. On the right side, you can see an integrative example mixing car design and its dynamics, the environment, and the driver actually piloting the car. Having an integrative approach involving the driver is the only way to assess your HMI thoroughly. VR is definitively the technology of choice for this. Now, today we are working with key clients on those challenges to define those solutions. And they are part of what we call at OPTIS an early adopter program. And this early adopter program deals with the following products in the OPTIS portfolio, allowing you to address those challenges. The first component is VRX, allowing you to have the vehicle dynamics, the ADAS assisted driving testing with sensors, and the mill, seal, and hill closed loop simulation. From another aspect, you have VIA, dealing with visual ergonomics in real time, including rear vision and reflection analysis. And you can also simulate your HUD in real time with optical considerations. And the last piece, the last component is HIM, allowing you to simulate the full body ergonomics, to analyze the full body ergonomics, including finger and head tracking. And as well, you need to interact with your dashboard, so you need the hard switch and touchscreen simulation component. Now, to come back on the early adopter program per se, I would say that it is a group of strategic partners who are willing to share their experience to help OPTIS to shape the next experience of VR simulation tools. The key challenges we have to overcome through that program are body ergonomics, virtual HMI interactions, and assisted driving technologies. And in return, this program will support you in innovating more by exploring new concepts, fostering collaboration among all stakeholders, improving quality overall by refining faster your design and avoiding mistakes and costly recalls, and finally, of course, saving time and cost by reducing physical prototypes and having leaner processes. We would be really delighted to have you part of that journey, of that early adopter program. Do not hesitate to contact us. That concludes our presentation, and we would be happy as well to answer any question you would have. Thank you very, very much.